Welcome to our deep dive into advanced Windows kernel debugging using WinDbg, specifically focusing on the Kernel Mode Driver Framework, or KMDF, and analyzing an Echo Driver. Kernel debugging is an indispensable skill for anyone working with operating system internals, driver development, or vulnerability research. It allows us to peer into the very core of Windows, observing how the kernel manages resources, processes I/O, and interacts with hardware. WinDbg, Microsoft's powerful debugger, stands as the premier tool for this task. It offers unparalleled capabilities to inspect memory, execute code step by step, and analyze complex data structures within the kernel. Today, we'll unravel the intricacies of a KMDF Echo Driver, a common example used to illustrate basic driver functionality. Understanding this foundational driver will equip you with the methodologies to debug more complex kernel mode components, providing insights into their behavior and helping diagnose elusive system issues. Establishing a robust debugging environment is the first critical step in kernel analysis. This typically involves two machines, a host machine running WinDbg, and a target machine where the driver under test, such as our KMDF Echo Driver, resides. These machines are interconnected via a debugging transport, which can be a serial port, a USB 2.0 or 3.0 cable, or, increasingly, a network connection for modern systems. For network debugging, you'll need to configure the target machine's boot configuration data, or BCD, using commands like bcd-edit-debug-on and specifying an IP address and port. On the host, WinDbg needs to be installed, ideally with symbol server paths configured to Microsoft's public symbol server to resolve function names and data structures. This setup ensures WinDbg on the host can communicate with the kernel debugger on the target, allowing for seamless breakpoint setting, memory inspection, and execution control across the two systems, forming the foundation for our advanced debugging techniques. The Kernel Mode Driver Framework, or KMDF, represents a significant evolution in Windows driver development. Introduced to simplify and standardize the creation of kernel mode drivers, KMDF provides an object-oriented, event-driven model that abstracts away many of the complexities inherent in the older Windows driver model, or WDM. This abstraction significantly reduces the amount of boilerplate code developers need to write and helps prevent common driver bugs related to I/O processing, power management, and plug-and-play, or PNP. Our focus today is on the KMDF Echo Driver, a quintessential example. Its primary function is elegantly simple. It receives an I/O request packet, or IRP, containing input data, and then echoes that data back to the caller. This straightforward operation makes it an ideal candidate for demonstrating how KMDF handles I/O requests and how we can use WinDbg to trace its execution path, inspect its internal states, and understand its interactions with the Windows kernel. Once our KMDF Echo Driver is installed and the system reboots or the driver is started, a sequence of events related to driver loading and device enumeration begins. As kernel debuggers, our first task is to verify that the driver has successfully loaded and that its associated device object has been created. WinDbg provides several powerful commands for this. The not_drv_obj command allows us to inspect driver objects by name or address, revealing details about the driver's entry points and its current state. Following this, not_dev_object helps us examine device objects, showing how the driver interfaces with the hardware and the I/O manager. We can also use not_dev_stack to visualize the entire device stack, understanding how multiple drivers might layer on top of each other. Furthermore, understanding plug-and-play, or PNP, is crucial, as KMDF drivers heavily rely on them for resource allocation and device initialization. By using these commands, we can quickly confirm our KMDF Echo Driver is correctly initialized within the kernel, setting the stage for deeper analysis. Tracing the execution flow of our KMDF Echo Driver is fundamental to understanding its behavior. WinDbg offers a versatile array of breakpoint commands to achieve this precision. The most common is BP for setting a software breakpoint at a specific address or function name. For hardware-assisted breakpoints, especially useful for catching memory access violations, we use BA, which allows us to break on access, write, or execution at a memory address. To set breakpoints across multiple functions or methods that share a common naming convention, BM for breakpoint by mask is invaluable. Beyond simple breaks, we can define conditional breakpoints, ensuring WinDbg only pauses execution when specific criteria, such as a particular IRP major function code, are met. Once a breakpoint is hit, commands like P, step over, T, step into, and G, go, allow us to meticulously control execution. Critically, K, or KB, provides a full stack trace, showing the call history leading to the current execution point, which is vital for understanding context within our Echo driver's operations. At the heart of any kernel mode driver's operation, including our KMDF Echo Driver, lies the I/O request packet, or IRP. An IRP is the fundamental data structure used by the Windows I/O Manager to communicate I/O requests from user mode applications or other drivers to kernel mode drivers. Understanding its structure and contents is paramount for effective kernel debugging. WinDbg's powerful NIRP command is our primary tool here. By simply providing the address of an IRP, NIRP address, we can dump its entire contents, revealing crucial information such as the major and minor function codes, the status of the request, and importantly, pointers to the I/O stack locations. These stack locations are particularly interesting as they contain parameters specific to each driver in the device stack. For our Echo driver, we'd examine the IRP-MJ device control, or IRP-MJ read/write IRPs. By tracing the IRP's journey through the various dispatch routines of the driver, we can pinpoint exactly where data is processed, modified, or potentially mishandled, making NIRP an indispensable command for I/O flow analysis. Beyond just IRPs, understanding the fundamental kernel objects that represent our driver and its associated devices is crucial. Every loaded kernel mode driver, including our KMDF Echo Driver, is represented by an _driver object structure. This structure contains essential information such as the driver's entry point, its registered dispatch routines, and a pointer to the driver's name. We can inspect this object directly using WinDbg's dt_driver object address command, which displays the data type at a given address. Similarly, each physical or logical device managed by our driver is represented by an _device object structure. This object holds details about the device's characteristics, its attachment to the device stack, and a pointer back to its controlling driver object. For KMDF drivers specifically, the WDF Windows Driver Framework objects provide a higher level abstraction. The @wdfkd.wd device and @wdfq.wdq extensions are invaluable for delving into the KMDF object model, allowing us to examine specific WDF device and WDQ objects. These commands provide a comprehensive view of how our Echo driver manages its devices and queues I/O requests, offering insights into its PNP and power management states. In the multi-threaded, preemptive environments of the Windows kernel, concurrency issues are among the most challenging to debug. Drivers, including our KMDF Echo driver, frequently need to protect shared data structures from simultaneous access by multiple threads, using synchronization primitives like spin locks, mutexes, and semaphores. When these primitives are used incorrectly, they can lead to dreaded deadlocks, where threads endlessly wait for resources held by each other, or race conditions, causing data corruption. WinDbg provides invaluable tools for diagnosing such problems. The .locks command is a powerful extension that enumerates all executive resources and spin locks, showing which threads own them and which threads are waiting. This helps us identify potential contention points or actual deadlocks. Furthermore, commands like .thread and .stacks allow us to inspect the state of individual kernel threads, including their current execution context and wait chains. By combining these techniques, we can meticulously analyze the synchronization mechanisms within our Echo Driver, understand how it manages concurrent I/O requests, and proactively identify and resolve potential threading issues before they lead to system instability or crashes. While WinDbg's built-in commands are powerful, its true versatility shines through its scripting capabilities and extensible architecture. For repetitive debugging tasks or complex analysis workflows, scripting and WinDbg can significantly boost efficiency. The .script command allows us to load and execute debugger scripts written in languages like JavaScript or VBScript to automate actions such as setting multiple breakpoints, logging specific events, or parsing complex data structures. WinDbg also supports loading custom debugger extensions using the .load command, often provided as DLLs. A prime example for KMDF drivers is the N1WDFKD.dll extension, which we mentioned earlier. This extension provides a wealth of WDF-specific commands such as N1WDFK.WDF driver or N1WDFK.WDF request that are invaluable for navigating the framework's object model. Furthermore, the .reload command is essential for ensuring symbols are correctly loaded after a driver recompile or module load. These advanced features empower us to tailor WinDbg to our specific debugging needs, enabling automated root cause analysis, custom data visualization, and a far more efficient debugging experience, especially when dealing with the intricate interactions of a KMDF driver. As we conclude our journey into advanced Windows kernel debugging with WinDbg and the KMDF Echo Driver, let's consolidate some best practices that will serve you well in any kernel debugging scenario. Firstly, always ensure your symbol server is correctly configured and that symbols are loaded for all relevant modules, especially for the operating system and your target driver. This is fundamental for resolving function names and complex data structures. Secondly, cultivate the habit of documenting your debugging steps and findings. Reproducibility is key. If you can consistently reproduce a bug, you're well on your way to fixing it. Thirdly, leverage WinDbg's logging capabilities to capture command outputs for later analysis, particularly when dealing with intermittent issues. Finally, remember that kernel debugging is an iterative process requiring patience and systematic investigation. The techniques we've covered, from setting up your environment to analyzing IRPs and using advanced extensions, provide a robust framework. Mastering WinDbg and understanding KMDF internals will empower you to tackle even the most challenging kernel mode problems, ensuring system stability and security. Keep practicing, and your expertise will grow exponentially.